Hey, here's your TA. Hey, Dr. Raver.
Hey. Oh, no problem. I was just going to let you know that this is the last meeting for the class, so there's no formal lab.
Okay.
So feel free to do what you want.
All right. And so next time we get together in 2 weeks will be the final exam, correct?
Right. Yeah. So I'll send you down a copy of the final exam to hand out. If you could proctor that during the next time, that'd be great.
Okay. All right.
All right. So I think I already did this, but
I did.
all right. So couple of things. First, I announced this last night too, but now we have 2 graduate students here anyway. But and you were here last night, and so there's only like 3 people here that didn't hear this last night. But one of the courses I'm teaching next semester is GHY 715, and I know that some of the graduate students are already in it. But I was talking with
graduate students are going to be signing up for it today, Dr. Raver.
all of them. Oh, okay.
We learned that yesterday.
Oh, okay, great. Well, yeah. So there'll be more people. I was also talking with David yesterday, and we're going to make the course available for undergraduates that want to take it as well. So it's a course, if you're a GIT major, it will substitute, because right now there's a course that you have to take in psychology or sociology. You have a choice between taking 2 statistics courses over in psychology or sociology, and you can still take those if you want to, or next semester you could sit in 715 and do the 715 work, and you would be taking GHY 492. So I have a 492 section, and you can sign up for that 492 section, and it will meet on, what do we decide, Wednesdays? It's the same time as, unfortunately.
It's 1 o'clock, and I think it's, I don't remember what day it was.
Yeah, let me look that up one more time.
But yeah, unfortunately, it's like directly in the way of
Yeah, it is at the same time as Capstone here at this campus. But
for graduate students, that is a requirement. So.
That's what I understand. I had heard that it was I'd heard that it was a requirement, but now I got some conflicting information, so I thought it was a requirement, but I don't know for sure. So yeah, next semester, just making sure I know what time it is. Next semester, that will meet at 1 to 3:45 p.m. on Wednesdays. So I have this section of 492. Right now, there's nobody in it, but that will be, if you sign up for that, you'll be responsible for this course. I mean, the undergraduate students won't have to do quite as much work, but it's basically a course in statistical analysis, but looking at geographic data. So there actually is a unit. So there is some overlap with this class because there is a unit on spatial autocorrelation and that aspect. But all right, so I'm going to close that up. So that's it for that announcement. If you have questions, let me know. I went through and looked at everybody's assignment for their final project proposal, and I provided feedback. Some was short, some was not as short. So you should be well on your way. I didn't think that there was anybody that was like going down a path they shouldn't go down. They're all they're all at least a good start. What I could say about that. And so if you have questions as you work through these over the next couple weeks, please let me know. And you know, if you want an opinion on what sort of analysis you can do to ask a question, I'd love to answer it, and I'll walk through it with you. So, see if that works. It doesn't. I did add just a little sentence here. So this is where you'll turn in your final assignment. I did add a little sentence here that says one of the end results will be a map, because I didn't specifically say that, but that I think that should be implied by how I described it last week. So you should turn in at least one map as your final project, and so I think that in some ways that might guide you on your path to completing the project. If you think about what it is you're trying to show, because a map is a communication device. You're trying to tell a story, or through a series of maps, you can tell a story. So you feel free to include more. Okay? You also must turn in a report. The report then this is all the same as it used to be. Okay. The due date is what we discussed, right? December 11th? Okay. All right, so another thing is that I realized that most of the stuff didn't stay published, but the review guide from the last time I taught the course stayed published. Here's what you see on my end. So I unpublished that review guide. So if you've looked at the review guide before today, there's a lot of similarities, but there's some differences. So please re-download the review guide if you haven't already. So you should only see the one that says Final Exam Review 2019 now. So that's the one that we're going to go through now. Oh, by the way, I just brought this. This is going back to that announcement I made about the class, 715. So this is the book for the class. It's not super expensive, but it is a book that I've seen utilized even in 300 level courses. So don't be afraid of the content because it's numbered 715. All right. All right. So I'm going to download this.
And that date is the date that we are having our final exam, Monday, the 4th.
Right. So for this class, and now I guess it's the policy of the university. Sometimes I tell a story and I think I already told the story, but once a week classes are. I can pull up the webpage to prove it if anybody wants to, but once a week classes now are supposed to be on the final day of class, is the final exam. And it used to be that our classes would always conflict because we have a bunch of once a week classes in this department. And so we'd be like, I'm giving my final exam, and then they're like, no, I'm giving my final exam. And so I guess the university got wind of it and made this change. So last day of class is the final exam. So what I've done to adjust that is just make to adjust for that is to make the final projects due after the final exam, so that you have enough time to do all of it.
Then should it be on Wednesday? Yeah, last day of class.
Oh, does it say? It says Monday, but it is Wednesday. That's a misprint. Yeah, that's a misprint. It's still December 4th.
The comment online says you don't see the proposal, but I mean it's turned in on my side.
The proposal part? Okay, we'll talk. We'll do with that after class. I didn't see it. Did if I go to I'm gonna have to edit that out later, aren't I? Okay. But yeah, I'll do that. I'll do that later. So Word. I meant to pull up that page, but you can't get there without going to the grades page. Okay, so I'll just change this real quick. I just shouldn't put a date. I mean a time. So it'll be December 4th. That is the correct date, but I messed up and put the wrong day. So it's not going to be Monday. I did. When I was an undergraduate, I had a dream that I kept having dreams that I'd show up for the wrong time for different things, including exams, right? So nobody show up for the wrong time. One time in my 15 years here, it was back when Skeeter was the department chair, Dr. Dixon. One time he called me up and said, your class is here waiting to take their final exam. Where the heck are you?
Oh, really?
Yeah. So I forgot once. I won't forget.
To note, it does say 11:30 p.m., but I will be here at 11:30 a.m. To know.
All right.
So that night was-
I'll fix that. Yeah. Sorry about that. You got another question down there?
I did my best work for 12 months.
You got a lot of good stuff done. All right, so so final exam, same format as the midterm. So mostly short answer. There actually is some more. I'll get into this in a second, but there are some questions that are more multiple choice like, okay, which is different because I don't think there was any of that on the midterms, but particularly in the structured query language part. Yes, you will. So we are going to focus, lots of people, one of the questions people always ask is it's going to be cumulative. Okay. It will be cumulative in that some of the concepts build on each other. For example, when you're doing spatial autocorrelation analysis or doing any pattern analysis, oftentimes to get that data, to get the data that you're analyzing, you've done some sort of overlay or spatial join to get to that place, right? So in that way, it's cumulative. And so you should still be able to understand those concepts, but we're not like directly testing you on those concepts again. So there's not like another test question on what does this look like after an overlay has been performed, things like that. Sorry, did you raise your hand?
I was just going to tell you that for the final project, I give you the proposal, and I kind of plug the data into and I was looking at the attribute table, and the data wasn't like completely accurate. So I was just going to tell you, I probably got to change that. I was just going to tell you I was going to kind of look around on Maris and come up with a new idea and email you that.
Okay, yeah, that's fine.
That's
fine.
Yeah.
Yep.
Yeah.
Totally fine. I'm glad you're on the path there. All right, so yeah, okay. So let's talk about the content of the review guide. I did make up the test mostly already, and so I can speak to what's on it. I'm going to sit down over here because that way my voice will pick up on the video better. All right. So I divided the section up into the longest one here is spatial pattern analysis because we spent a few weeks on it. And then we talked about correlation and regression, and we talked about spatial SQL. And then finally, last week, there's not a whole lot of questions on this, but we did discuss the classification of spatial data a bit. Okay. So that's where we are. And so the first topic that you'll need to understand is basically just when we talk about spatial pattern analysis, what are we referring to? And specifically, we discussed two different properties of spatial patterns or spatial phenomenon. We talked about there being first-order properties and second-order properties. And so on the test, you will either need to provide examples or be able to recognize examples of properties that fall into these patterns. So how do we define the difference between these two? So the first one is how a spatial pattern is related to another. And I noticed a couple of these types of questions, types of patterns that you all were looking for in your proposals. So what are some examples here? So if we have information on the distribution of some variable or some entity, some real world thing, and another variable in the real world, and we want to examine, are they related? Do they exist in the same location? Okay. So if I were to try to find out if trees were taller near water, that would be an example of a first order property. If I wanted to find out if a certain species was affected by the presence of human activity, that would be another first order property. So looking at how it is affected by another spatial variable. Okay. Oftentimes, those questions are answered through doing an overlay or a spatial join. I guess in reality, it's the first step in answering those processes, right? So overlay, spatial join allow us to examine the presence of two different things and look and organize them into the same attribute table. Okay. So that's a first order property. And then, that was a lot of what we spent the first half of the course discussing. Not everything. Network analysis is, well, it's kind of like that. It's a network analysis, and really one way to look at it is it is an alternative way to quantify how far away things are from each other, or to quantify not how far, but how connected things are. Okay, so I got off on a little bit of a tangent there. A second order property is how a spatial pattern is related to itself or a distance from other observations. And that's really where we get into quantifying that through spatial autocorrelation. Second order properties are quantified through spatial autocorrelation. So it tells us, spatial autocorrelation analysis is for looking at the pattern of a particular variable on the landscape. So we're actually, instead of looking at how one variable is related to another, we're looking at how one variable is related to space. And you can see that when some of the ways that some of the graphs that we brought up with when we first started to explain spatial autocorrelation, that was the x and the y axes, the value and its neighbors. So in other words, space. Okay. Yeah. Go ahead.
Another example of second order property.
A second order property. So if we wanted to find out, well, oftentimes we're asking whether or not something is the pattern that it exists is random or dispersed or clustered. So another way to say that is, do shopping centers tend to be located near each other? So that would be saying, another way to say that is, are shopping centers clustered? Oftentimes, a second order property will have in its thing either something about pattern or something about how a variable is located, how a variable is related to itself spatially.
So is the main difference really that a first order property, you're looking at two things together like soil type and plant type versus looking at just one very variable being the second?
Right.
Order? Okay.
Yeah. A first order property, it doesn't actually have to have, it can, but it doesn't have to have anything spatial about it. In other words, the only thing that's spatial is that they're co-located next to each other. So you're just saying, okay, this is next to that. Now how you define next to might involve using space. But a second order property is looking at how a variable is related to itself, and it has to include some measure of space, because how you talk about being near something. It has to be something about space. Pattern and space are related in that way. All right. I may have been a little bit scattered on. We may go back. We're going to definitely go back to autocorrelation, but some of this is how I answered the test question. I mean, how I laid out the test questions, and so I am going to go back and forth a little bit. But you should be able to define the terms mean center, median center, standard distance, and standard deviational ellipse. We talked about those. Those are also all in ArcGIS Pro. The mean center is probably the easiest. Okay, the mean center is just the weighted average of all the x's and all the y's weighted by their spatial location. So if you have a bunch of points, it's as easy as adding up all the x's, adding up all the y's, and dividing them by the number of points. Dividing the x's by the number of points and the y's by the number of points, and your mean center is the average of those values. Okay. So here's the median center, and with some of these, including this one, and I'll talk about some of the spatial autocorrelation measures later. You can go through, and just as helpful as looking at any other thing is the help topic that discusses it. So the median center is another measure of the center location, but it doesn't measure it by adding up all the x's and adding up all the y's. Instead, it minimizes the overall Euclidean distance to the features in the data set. So in other words, this point here has the smallest total distance to all the other points. It's actually similar, when we did network analysis, it's actually similar to the measure of centrality that we talked about, right? The measures of centrality. So here we're looking at the average distance to all the points, and this one, sorry, not the average, the total distance to all the points. So it's the dot that most close, well, that minimizes the distance to all the other points. Obviously, there's a computer algorithm that's implemented by ESRI to calculate that. You're not going to have to do that. Okay, nothing like that. All right. I think they're all in here. Standard distance. So this is basically the difference between the standard deviation, calculating the standard distance and the standard deviational ellipse, is that the standard deviational ellipse looks at both the difference in the x and the difference in the y and calculates them separately. So you're getting an ellipse. And with the standard distance, it's just the average distance. It's calculated as the average distance from the center to every point. So that's what this circle represents. Is the average distance from the center point, the mean center, to every other point. So that value represents, and it's shown as a circle.
And so it'll always be a circle since it takes x and y at the same time.
Right. Yep. So the standard distance is always a circle. The standard deviational ellipse is obviously not always a circle. It's in the name. Yeah. All right. We actually never implemented these in class, but we did talk about some ways to find the center of a polygon. And one way is like the one way that we talked about is, one way that we talked about the most is to basically, if you have a polygon, we talked about two ways. So if you have a polygon, basically the weighted average, if you could think of a polygon as being just a bunch of points, there is a center of mass of a bunch of points. The problem with that is if you have like a horseshoe-shaped polygon, the center of that polygon is going to be outside of the polygon. So ArcGIS, if you run and actually many programs like this, if you run a feature to polygon, polygon to point. I guess it's just feature to point. Feature to point. You have the ability to like check this box or not. And so if you don't check that box, it's going to find basically the weighted average of all of the polygon. It's going to put it in the middle of that feature. So if it's a horseshoe shape, it'll be in the middle, and it won't be. Or even if it's a donut, right? It's a donut. Let's still put it in the middle. Okay? However, check this box. What it does, and I described this in class, and so you might have to replicate this on the test. What it does is it basically starts from the outside and erodes away at the polygon until there's just a little spot left. I need to close some of my windows, don't I? Some of these is probably just better to reference what I'm talking about here. That was in here. Yep, right here. So they call it skeleton to center. So you take the outside of the polygon and you don't actually see this, but what's happening is that it's progressively shrinking the polygon until you get to the very end, the very bottom. And it is possible in some very regular shapes to get to two centers. Like let's say you had like a figure, like a MasterCard logo. It would be possible to get two centers. And I don't know exactly how they compensate for that, but you won't see anything like that on the test. Okay. Okay, how to calculate point density. We calculated point density early in the semester, the density of the tornado observations or any other thing. Basically, you can do that through an overlay or a spatial join. How would you do it for an entire study area? Okay. Well, you could do it in a number of ways, but it still involves the same tools. But you need to come up with a total. You could do the spatial join first for all of your little individual areas, and then you could sum up that column to get the total. Or you could dissolve the entire area into one polygon, and then do a spatial join, and you get a total area. Okay. So what can it be useful for? It's often useful in determining the density. So it's a density measure. You're finding out how often something is occurring in a certain area. Really, these next two questions coincide with this. So we mentioned kernel density here. So what kernel density does is it usually produces a raster. It almost always produces a raster data set. So for every cell, it goes through and calculates the number of features within a certain radius of that cell. So that's how you calculate kernel density. So you give it a radius, and it outputs a raster where every cell represents how many features are in there. Oftentimes, it's the number of features per unit area. Okay. So this we didn't cover that much in class because this is a vector-based class. We did talk about quadrant density, and we did do that's basically what we do with the tornadoes and the hexagons. One thing that you should remember here is that when you're doing quadrant density, if your quadrants, just meaning polygons here, if your polygons are not all the same size, you definitely need to come up with some way to normalize them, usually by dividing it by the area. So you have a count per area. All right, now we're getting back into spatial autocorrelation here. So you should be able to define and recognize clustered, dispersed, and random patterns. Okay. Especially when compared to each other, like relative. Because I know one of the whole purposes, well, not the whole purposes, but one of the things we learned about in the course is, well, sometimes you can't just recognize, is it random or is it not random? Right? You can't just see it and know that it is random or not, and that's why we have tools for quantifying the degree to which a certain pattern is random, clustered, or dispersed. But if you saw 3 examples, such as what we showed on the slides, you should be able to recognize the differences between being random, clustered, and dispersed. This might be the wrong lecture. Well, this is.
Do you mean visually, like
yes,
like that, or you mean like the actual z-score and stuff like that?
Well, right now I mean visually, but you should be able to understand. You should be able to understand both. Yeah. So yeah, dispersed, random, and clustered. So the examples on the test will be like that, where it's fairly extreme. One key to a dispersed pattern is that there's almost the same number of observations everywhere, or they're regularly spaced. That's different than a random pattern. A random pattern will have some. It'll be random. It'll have some areas where the points get closer together and some areas where they're further apart. But the points will look like they're placed at random. All right. You should also be able to, this is what you were talking about, Ashley, asking the question. When we quantify spatial autocorrelation, I guess there won't be any z-scores on the test, but basically, kind of like this slide, you should be able to know that interpret positive and negative spatial autocorrelations and when they exist. Okay, so which one's random, which one's dispersed. So, and which one's negative. So here's a good slide for that. Positive spatial autocorrelation means that they cluster. Negative means that they are dispersed. And so random is close to 0. All right. All right, and then you should be able to understand the mechanics of how we could go about quantifying spatial autocorrelation. Like again, you're not going to have to do any formulas or not, but you should understand that that spatial autocorrelation is built through looking at the relationship between a variable and those values that are nearby it. That's of the same variable nearby. Now, how you calculate nearby is different, and you get to choose that as the analyst or the researcher. Okay? It could be the ones that touch. It could be with the ones within a certain distance of. That's why we talked about all the spatial relationships at the beginning of the course, right? But this scatter plot that we show here, okay, you should be able to interpret that scatter plot. So we're looking at a certain set of values as related to those values near it. All right, so that's a scatter plot. Now I talked about scatter plot. So what are the axes in the scatter plot that might be used for the autocorrelation? You should also be able to interpret a variogram. It's a little bit different axis. So this is a scatter plot showing spatial autocorrelation. And yeah, here's a variogram. And it does things slightly differently. The axes are a little bit different, where we have distance along the bottom of the axes, and then so these are the distance between. These are the differences in values between points that are very far away, and the differences in values between points that are very close. So the average distance in the values for geographic locations. So if this represented income, let's say, and these were census tracts, then if this looked like this, what's happening is that census tracts that are nearby one another have similar values. And as you get further away, census tracts that are further away have some similar values, but also some very different values. And so almost all scatter, if there is spatial autocorrelation, you look at a variogram, and there is spatial autocorrelation, it will be tightly clustered until some point where it starts to disperse. And at that point, that we call that the range. At that range, there's no longer any relationship between that variable and space.
So you said near the center point or near the corner is the most related ones on this type of graph?
Yes. Yeah. As you move this way, but yeah. So this is distance. So every dot represents a pair of features. So if these represent census blocks, every dot on the map, every dot on the variogram represents the difference between two different features. So if that feature is really far away, it will appear on this side of the map. And if they have the same value, they'll be closer to being on this side. If they have a very different value, they'll be up here. So this is distance, and this is the difference between the values. So, for example, if we go back to the census tract, if you have two census tracts with the same income, the exact same income, and they're very far away from each other, that dot would be down here, okay, way down here. If you have two census tracts that are very close together, but they have very different values, that dot would be up here, because this is distance, okay? If you have two dots with similar values that are close together, over here, if you have two dots that are further away with different values, that dot would be up here. So that's how you interpret that variogram. So from this, there's a couple of things labeled, but really, besides understanding where dots would appear on the map, and why it would look like this, the range is the only thing that you really need to know what it is on this. You don't need to know. You really need to know what the sill is. The range is the only thing on the test. Okay, and
You
that's
said the range is the point to where the spatial autocorrelation stops? Or
yeah.
no
It's the point to which there's no longer a relationship between that variable and the space and distance. That's another way to say that. So you could say beyond that range, there's no relationship, there's no spatial pattern that exists. There's no relationship between that variable and itself.
Would that be like if you was comparing snow to elevation, and then once you exceeded the elevation of the highest mountaintop, there would be no snow, so there would be no correlation?
Well, this would be looking at the presence of a single variable, so it wouldn't be snow and elevation. So you could say, well, we could just have elevation, just elevation on here. So it's elevation and distance. So if we did just elevation, the elevation, let's just think of the side of a mountain. So if we only had the side of a mountain in our study area, then, and it's just constantly going up, or going up, not just constantly, but it's going up, yeah, I guess constantly is a good word, but it doesn't have to go up. It has to just trend upward.
Right.
As long as it trended upward, then the value of elevation at any particular point and its neighbor would be pretty related. There wouldn't be much difference between being here on the mountain and being here on the mountain, right? So those points would be down here. But as I got further away, the difference between being here on the mountain and 10 miles further up the mountain would be a lot. So those points would be up here. But what would be interesting is that there wouldn't, in that scenario, there wouldn't actually be this spread. It would just keep going, and there would be a relationship, and that would be shown on there because all the dots would stay close to the line. They'd all stay close to the line. As you got further away, we're still able to predict, because there's a trend going upward. There's nearly a constant slope. We'd be able to predict what the elevation was 10 miles away within a little bit. Okay, basically how spread apart this is tells me how well we could predict that value over in that area. So in another example, if we had undulating terrain, we could do that for just a little while, but then at some point we have no predictive ability, as to whether or not we could predict the terrain, and it would start to look like this. Oh, well, 10 miles over there, there's a valley. 10 miles over there, there's a peak. 10 miles in that direction, I'm about the same elevation. And 10 miles that way, there's a huge peak. So that would show that spreading out.
So that's like, that'd be an example of like a hurricane path. Like you can, the closer it is to it, the more likely that path is accurate. But then the further it goes, the path starts to branch out because you can't correlate anymore. Or quantify it.
Yeah, I mean that has more to do with just the uncertainty and all the other variables. Like, because a hurricane path is determined by, all the other atmospheric conditions. Right.
So is a variogram measuring a second order?
Yes.
And a scatter plot's doing a first order?
No, they're both measures.
Oh.
Well, okay. The last two. So a variogram is always showing a second order. A scatter plot is a generic tool, but this scatter plot is showing the same kind of relationship, and it's a second order relationship. But you could, like when we did regression, and we put in the average day since the last spring frost, and we put in elevation and distance to coast. Those were the variables. those scatter plots that we were looking at, when we looked at the relationship, I think I actually have that open from last night. So this scatter plot right here, which shows the northern latitude, the latitude, and the average date of last spring frost, this is showing a second order pattern. So scatter plot is like a general tool that can be used for either one. But if one of these two axes has to do with what we call the lag, remember I used that term, but if it has to do with space, so if this was latitude and then the latitude of nearby observations, that would be silly, but that would be a second order. If this was the average date of last spring frost and the nearby average date of last spring frost, that would be spatial autocorrelation. That'd be a second order. Does that make sense? Second order spatial process. So we'd be trying to investigate. We'd be trying to investigate if the last day of spring frost influenced the last day of spring frost of its neighbors, which, yeah, space could be a lurking variable in that, but it's not an explanatory variable. In other words, we would know that the last day of spring frost here wasn't causing the last day of spring frost over there to be the same, but it would still exhibit a spatial pattern as if it might be. But really, what's causing it is the things like latitude and the warmth of the climate and things like that. Okay. So usually when we're talking about a second order spatial property, is that we're thinking about the relationship between that and itself causing something. So in other words, does the presence of a store attract other stores to build near it? Okay. So a big store might cause people to want to put other stores near it. That's a second order property.
So each time you go through latitude layers, you have a delayed effect. As it go up, it's going to get a delayed effect. Every time it goes up, it's going to be delayed from the previous one. That's why the ones, as you start an equation going up, you get a delayed effect. And that's the second order effect also, right? Is that space in between those times, is that called a second order effect?
Yeah, second order effects are looking at a variable as it's related to itself spatially.
Okay, as it relates to itself. Because at one point it was here, at this point it's there. So you're comparing what it was and what it is now. Comparing it back to itself. That's the second order, correct? You're comparing what it was to what it is. That's the second order effect, right?
What it was?
Was here, or where it was here to where it is now. Why was it changed like this? The second order effect shows that its relationship from where it was before to what it is now. You know what that means?
Yeah. I mean, I think of what you're saying. So
you're comparing it to itself, as you said, comparing it to itself, relationship.
Right.
And like, in order for us to know that it's like this week, next week the rain gonna come, but this week is not. Why is it coming next week?
Well, you can have temporal autocorrelation, but we didn't really discuss that too much in our class. I'm talking about spatial autocorrelation. So in other words, we could make a map, a graph like this that had rainfall, and then rainfall, this graph could be rainfall a week later. And it might be that there's a relationship. If there's rain one week, there's usually rain the next. So something up here in the high, something on this side would mean that they had high rainfall one week, and then they had high rainfall a week later. Here, this would mean that they had low rainfall one week and low rainfall the next week, if we did a graph like that. And then anything up here would be That would be high one week and low the other, and this would be low one week and high the other. So if we wanted to measure the correlation, we could do that. And if we had a strong correlation, what that means is that areas that are dry one week tend to be just as dry the next week, and areas that are wet one week tend to be just as wet the next week. So it's not spatial, but it's still autocorrelation.
But is it time?
Auto.
Time,
What's
time
that?
Is time a factor in correlation too? Or time is not always a factor, because it can be dry 365 days a year by time, but what makes the correlation?
Correlation is just looking at the degree to which one variable co-varies with another variable. And if that one variable is a different variable, it's just plain old correlation.
Okay.
If that one variable is itself but lagged for time or lagged for space, it's autocorrelation.
Okay.
And a scatter plot is good for showing all different types of correlation, whether or not it's autocorrelation or just regular correlation. Whereas a variogram like this is more a tool for showing autocorrelation. So this would be distance, and that's the average difference in the locations. So this has all of the different pairs that are possible on the map. The difference between that and a scatter plot that shows autocorrelation is that the pairs there represent its value compared to its neighbors. This is its value compared to every other value.
And can you say if you find a bullet, would it can't go on the same trajectory, it might start dropping down, but it's a different type one that's lighter and it keeps going up. So you start seeing how range and distance has something to do with the pattern of how high the bullet goes up.
I don't know.
Well, I was in the trajectory. If you shot a light round, it's only going to go up and fall down. You got a powerful one, it's going to keep going up. Everyone different based on the speed, the power, whatever come out of that. So I was looking at that plot. That's how a trajectory of a bullet does. You shoot, it don't keep going up. It starts falling. Why is it falling at this pattern? Because it's...
You mean in the variogram?
Yeah.
Okay, so the line that's fit to this is just the line. It's a polynomial, it's like a first order polynomial that just has one curve in it. So it's still trying to, just like the straight line, it's trying to fit the best fit it can to these dots.
Right.
Okay. So we talked about a few. The first week that we talked about spatial autocorrelation, we talked about a few basic ways to measure spatial autocorrelation, and they were more about just measuring it rather than doing a hypothesis test or testing it. And so we talked about the variance mean ratio. Okay, so that one here. The variance mean ratio is simply we do a quadrant analysis, and with the variance mean ratio, we just take the average number of points per quadrant and the variance of points per quadrant, which the variance is just the standard deviation squared. Okay, so you don't need to know how to calculate mean or standard deviation, but it's the variance and the mean. It's the ratio of the variance and the mean. Per a number of points per quadrant.
So the variance divided by the frequency?
The average number of points. So if there's 5 points, yeah, okay. So if there's 5 points in one cell, 2 points in another, 3 points in another, and you're only using 3 polygons, then it would be 5 plus 3 plus 2 divided by 3. That would be the mean.
You just said that we won't need to know like practical application of the test.
You won't need to know how to calculate mean or variance, but you should know that the mean variance ratio is, or sorry, the variance mean ratio is the variance divided by the mean. And if it's close to 1, it's random. If it's close to 0, it's uniform. And if it's significantly higher than 1, it's clustered.
So close to 1 random, if it's close to 0, it's
Uniform.
dispersed.
Yes, uniform or dispersed are interchangeable terms. And then clustered. All right. And then the ANN analysis, which is actually implemented in ArcGIS. The variance mean ratio is not implemented in ArcGIS. I mean, you could do it. You just do a spatial join, and once you do a spatial join, you take the join count column, and you calculate the mean and the variance of the join count column. That's how easy it would be to do it. So it's not hard, but it's not like it needs a button, is what I'm trying to say, because it's only 2 steps. But there is one for the average nearest neighbor analysis. And what average nearest neighbor does is it calculates the distance of every feature to its nearest feature. And then it calculates the average value of those nearest values. You could do this. You could do this without a specific tool, because you could use the near tool and then calculate it. But there is a average nearest neighbor tool already, so you can read more about it. But basically, it is also a measure of being dispersed versus clustered.
You said it calculates the average distance?
The average distance to the nearest neighbor. So if it's clustered, that average distance to its nearest neighbor gets smaller. And if it's dispersed, it gets to be a larger value. And what it does is compare that. It's going to compare that. If you look at the slide here, it compares the average distance to the nearest neighbor to what it would be in a situation where it was totally uniformly distributed within the study area. So one of the disadvantages to the average nearest neighbor index is that it's dependent on the size of the study region.
So it's not a consistent grouping. It was like using counties versus our hexagon or our octagon.
Right. So the variance mean ratio, and then later, that builds on the LISA analysis, the local measures of spatial autocorrelation, the local indicators of spatial autocorrelation, the Moran's eye stuff. That uses quadrants or arbitrary polygons. So it's based only on the mean distance to the nearest neighbor. The big weakness here is it's very dependent on the size of the study area. Okay. So this slide is important, and this is on the test. That one right there. That part of it is that it's dependent on the size of the study area. All right. Why is it important to measure spatial autocorrelation? I think we've kind of talked about that, but basically, what does spatial autocorrelation tell you? And that is that it tells you that it tells you if a particular spatial pattern that you see on the landscape is the result of some second order spatial property, or if it's just random. And it can also tell you the nature of that spatial property, whether or not those things tend to not be located near each other, they're dispersed, or whether they tend to be clustered, whether they tend to group together. So how can a neighbor be defined when measuring spatial autocorrelation? So in almost all of these tools, not in the automatic, the average nearest neighbor, but in the, well, even here you can specify that the distance is a different type of distance. We don't really cover that though. But in most of the other measures of spatial autocorrelation, like this one, there is a method for conceptualizing the spatial relationships. So you could specify that they are based on distance, usually inverse distance. In other words, you would expect them to be more related if they're closer together and less related if they're further apart. You might expect them to be related if they touch, whether it's on the edges or the corners only. But that's what we're talking about here. How can a neighbor be defined? So a neighbor can be defined within a certain distance, or a neighbor can be defined based on a spatial relationship like contiguity, like edges matching or adjacency. How do we expect that to change the relationship? Sorry, you about to say something?
I was going to ask them, aren't there different ways you can differentiate, like how they touch, whether it's like by point or by edge or something like
right.
that?
Yep. Yeah. So here you do have whether they touch only on the edges or whether they touch on the edges and the corners. Then, so how do we expect that to change the measurement? Typically, when you whenever you correlate something and you include more data, you'll get I should say this.
It's like the pattern of trees on a certain landscape, how they spaced apart. You have to do with the pattern.
Yeah, but typically when you average more data together, when you're doing correlation, you'll get a higher degree of correlation. And so when you say, I'm going to compare just the neighbors, you might see less correlation typically than if I compare the average within 10 miles, a certain distance. So typically you see stronger correlations the more you average your data.
You see more correlation the less you average?
The more you average your data. I don't even know if there's a test question on that, but I'll find out. I'll go back.
Based on a big study area, I guess.
Yeah.
Larger study area would help the numbers.
Yeah. All right, so shape and landscape metrics. So we did talk a little bit about this. I was going to do a lab on it, but I didn't get that one made. But that's actually not this week. Oh yeah, here we go. Spatial pattern, landscape metrics. So landscape metrics basically look at a shape and try to quantify how irregular or how different it looks. Okay, so we can talk about one of the very common shape metrics is the compactness, which is just the perimeter to area ratio, the ratio of the area to the perimeter. But also you could compare a particular shape to a ideal shape, like a square or a circle. So the area of the perimeter of a circle, sorry, the perimeter of a shape and the ratio of the perimeter of a shape to an area of a circle of the same shape.
It was perimeter to area ratio?
Yeah. Now, we didn't really talk about this. This isn't going to be on the test. Let's see if I added. Yeah. So shape and landscape metrics quantify the differences in the shape of features. We did talk about that. But yeah, I don't talk about this contact number stuff in the study guide because I think I breezed through it in class. That's slide 37. Okay, measures of spatial autocorrelation in polygons. So this is the time where we went through and we talked about specific tools that are implementations of computations that we discussed. So we've got the global eye. When do you use that? Well, the global eye, it doesn't produce a map. What does it produce? What's that?
Like it produces like an out table stat.
Yeah, so basically it just produces a few numbers, and those numbers range from -1 to 1, and then there's also some information about the significance. But that information tells you whether the entire data set is clustered, random, or dispersed. So we're not looking for specific areas. We're just wondering if this data is clustered, random, or dispersed. That's what the Moran's eye does. The G statistic, the general G statistic, the general G statistic, which isn't run as often, tells you whether or not it's clustered or not clustered. Okay. It tells you whether or not it's clustered or not clustered, and whether or not you've got a lot of high clusters or a lot of low clusters.
But it's on the complete data set too.
It's on the complete data set, right. And so you could run, if you did these like it as a chain, you could run Moran's eye global to figure out if your data was clustered, random, or dispersed. Then, if you were curious to know whether or not there was a tendency for high or low clusters in your data, in other words, which one dominates, the high clusters or the low clusters? The values that are high, there's basically, high income areas. So first one I might want to say is, do people cluster by income? I run it through Moran's eye. I get an answer. Yes, your data shows clustering. Then I could run it through the Geddes or general statistic to ask the question, is this area dominated by people of high income clustering together, or people of low income clustering together, or is it all just kind of in the middle, high income and low income both cluster? That's the set. That's the way I answer that question. That's
so that one said, where?
Neither one of these do where. So
Neither?
These are both the general that we're talking about so far. And there are local indicators for both of these as well. So there's basically 4 different tools that we're talking about. The general versions, which look at the whole data set together. One is it random, clustered, or dispersed? That's the local Moran's eye. The global Moran's eye. And then whether or not the clusters are high, dominated by high areas or low areas. And that's the global G statistic. And then finally, the 2 local statistics. And the 2 local statistics show us on the map where clusters are occurring, and then it'll show you it'll show you the high clusters and the low clusters. That's the local G statistic.
So you wouldn't run a general G that tool unless the data set was clustered. You wouldn't run it on a dispersed data set, correct?
Well, there wouldn't. Yeah, I mean you could. It's possible, but it's to identify what type of clusters are dominating your data set. And so, no, you would not typically run the GETUS G statistic on a data set that wasn't clustered. Maybe there's somebody that I don't know. I'd have to like read some literature, but there could be somebody that decided, well, even in a case where it's dispersed, it's still interesting to see whether or not it's just slightly dominated by high or low clusters. I don't know, but typically from what I've seen, yes, you do not. You find out if it's clustered first, and then you run GETUS statistic to find out if it's dominated by high or low clusters.
And then the local to find out where they're actually at.
Yes. Yeah. So there's a lot of slides on that, and then also I'll go over here real quickly the tools that correspond to this. I'm just going to bring up the.
So when you talk about clustering, are you trying to analyze the 7 convenience stores in this one area and find out are they in a low cluster or high cluster area compared to one another, like that example that we do in the class?
Well, you'd be asking about whether or not convenience stores were located nearby each other, or whether or not they were dispersed across the landscape evenly.
Right, patterns, right. Are they all in one area or they spread? Is that the relationship you're talking about?
Yeah, if I had the location of all of the Walmarts, then I could use these tools to identify or examine those values. Now these tools look specifically at the attributes of the data, and if you don't have any attributes, then it's just going to use the count. So, like let's say you had a bunch of polygons, and in those polygons, a bunch of hexagons. In those polygons, you had the count of the number of Walmarts in that polygon. That would be something you could run through these analysis. But yeah, so if you want to, so for further reading, here I'll go the order we talked about them in. So we've got the global Moran's I right there. Okay, we've got the GETUS order G statistic right there. So run this one to find out if it's random, clustered, dispersed. Run this one to find out whether or not you've got high values or low values dominating your clustered data set. And then if you want to actually make some maps of where those are, you've got your hotspot analysis right here that identifies areas that are statistically significant, either hot or cold. You'd expect that if you got an answer for running this tool and it said you had your area was dominated by high values, you'd expect when you ran this that you would see some statistically significant hotspots throughout your map. And then this statistic is the is just looking at the clusters, whether or not they're high or low. Your statistically significant clusters. It calls them hotspots or cold spots, but what it's saying is it's going to do both rather than provide one or the other.
So what would cold spot be? The low?
Yeah, cold spot means that whatever value you're measuring, its nearby values are also low. A cold spot means that the variable that you're measuring has low values and its neighbors also have low values. So like in the tornado analysis, if we ran that through and we wanted to see the low spots, those would be areas where there weren't many tornadoes and there weren't many tornadoes even in the neighboring areas. That's a cold spot. Okay. So the next section now, move on to the next section. We're talking about negative and positive correlation. So you need to be able to recognize examples of that, things that are negative and positively correlated. Basically, this isn't the exact same slideshow, but basically the slide that looks like this. You need to understand that just because two things are correlated, it doesn't actually imply that one is causing the other. Although oftentimes we're looking for causal relationships, it involves scientific research to find out if there really is a causal relationship between two things. Correlation is just a tool for uncovering whether or not there is a relationship between them. But you have to actually have a reason for establishing that one is causing the other. Okay, basically what I mean by this next one, correlation in geographic data issues, is that you need to be aware that when we're looking at two different variables in geographic data, it could really be that what's causing the difference is a spatial autocorrelation effect. What's causing not a difference. What's causing a relationship is really a spatial. In other words, these two variables may both be related to the same thing. So one thing there would be going back to our average date since the last spring frost. So latitude and the average dates of the last spring frost are related. Elevation and latitude are not related to each other, right? Those aren't related to each other. You get high areas as you go up north. You get low areas as you go up north. There's no relationship between latitude and being north or south. So those are totally unrelated. But as you go further north, you do get colder. But there's going to be a bunch of other things that happen as you go further north.
Distance and space, distance from where it's hot from the equator to the north is
okay,
colder.
Yeah. Here's a better example. If we were just studying Mississippi, right, and we were looking at temperature in Mississippi, we might find that temperature in Mississippi is related to distance from coast. But in reality, there's not really a connection between those two. The real difference is that as we travel more northerly in latitude, we have less sunlight and the temperature changes as a natural effect of that. Okay? So that's an example where with geographic data, we may see a correlation between a variable and one variable, but it may be that it's just another variable that's by accident related to space.
Would our sea level change too? If we go from where we are now up north of the city, your elevation change.
Yeah, elevation would change. Yeah, that's another thing. For Mississippi, distance from coast is probably related to elevation pretty well. There's probably a pretty good relationship between distance from coast and elevation. But does that exist everywhere? I mean, my dad lives when I grew up in Southern California, he's moved since, but he lives in this beach city. He lives at a higher elevation. He lives almost at 1,000 feet, but than I do, and he lives, 10 feet, not 10 feet, sorry, maybe 2 miles from shore. Maybe not even 2 miles. A mile from shore, he's already 1,000 feet. We don't even have 1,000 feet elevation here in Mississippi. So it's just because two variables are related spatially in space doesn't mean that it's one's causing the other to occur. All right, so you should be able to interpret some simple linear regression algorithms. Specifically, you should be able to understand what R squared is and what a residual is. So R and R squared are the degree, the amount. R squared is the ratio of variance that's been explained to the unexplained variance. So in other words, it's how well these two are related to each other. Okay. In other words, can you predict one from the other? And that's the strength of association. And then a residual is the difference between a single observation and the overall pattern. And so if you looked at a map of residuals, the high residuals are the ones that don't follow the trend. And the low residuals also don't follow the trend. So the ones around 0 follow the trend. The highs and the lows don't follow the trend. Sorry, what was you about to say?
I was going to ask if you could repeat the definition for R squared.
Oh, yeah, the R squared is the ratio of explained variance, and I said the unexplained variance. It's the amount of explained variance divided by the total variance of the two data sets. But what you need to do is be able to interpret it and say, okay, well, this relationship is stronger than that relationship.
The residuals is how different, like one
observation from the overall trend. So in linear regression, you're going to get a line, right? And that line is created as the best fit of a scatter plot of data. So the difference between each observation and that line is the residual. Okay, both of these are really related to the same concept there, and that is the part of the slideshow where I went over the 6 statistical checks to go through for a properly specified regression model. Okay, so I don't have that slideshow up. Yep. So starting right here, creating a properly specified regression model on the 6 statistical checks. So here, yep, well, I guess we can just go through each of them. First you look at whether or not each variable, like in multiple regression, you look at whether or not each variable is significant to the model. So that's mostly what this is about. So the test question will ask that. So
you know, like what number on an output report tells us that, 'cause that's what I get mixed up the most. Like, I understand the concepts of, oh, you gotta check to see which variable is more, statistically significant, but do we have to know, like, the OLS number tells us that, things like that nature?
No, basically, you just need to know whether or not, basically what you need to know is that you should check each of the coefficients to determine if they're statistically significant, not how to do it. That's all that's on the test.
Okay.
And then looking at whether or not they're positive or negative, what that means. If they're positive, that means that they have a positive spatial relationship. I mean, not spatial, a positive relationship. And if they're negative, they have a negative relationship. In other words, as one goes down, the other one goes up, is negative. They both go up together is positive. That's the way to say that. Okay. And then the statistical check 3 looks at, are some of the explanatory variables telling you, are some of the explanatory variables telling you the same thing or not? So really, if you know that, you're fine. One variable may be telling you the exact same thing as another variable. And if you do that, what's happening is that you're biasing your regression equation by including by basically double counting, making something twice as important as it should be. And then yeah, so this next one determines whether or not your residuals are normal looking. So okay, so there's a lot of terminology, but basically what this is telling you, let's see if I have an example. No, I don't have an example. You always have a mean of 0. Okay, like let's say that I had a scatter plot for some reason that looked like this or this, either of those two, right? And I tried to fit a line to that data. If I tried to fit a line to that data, I would see that my residuals started out maybe very close to the line, and then they got big, and then they got small again. If this line went right through here, so my residuals got big, small, and big, or something like that. Okay. What that means is that regression isn't the right tool for solving this problem. So we're on 4, by the way, now. So anytime where your residuals don't look like they are spread about spread evenly around the line, you've got a problem. That's what statistical check 4 is looking at. And then even if your residuals look like they're scattered pretty well, but if you map them and the residuals are high in one area and low in the other, what that means is that one of the spatial patterns that probably explains your process is a second order spatial process, or explains your result is a second order spatial process. And so you've got spatial autocorrelation. So one thing that when you do regression in ArcGIS, it will make a map of the residuals. And then you can take that map of the residuals and find out if they're random, clustered, or dispersed. And if they're clustered, that's a problem. That means that you should either run geographically weighted regression, or you should find some spatial variable to throw into your regression equation. So that's what statistical check 5 is looking at. It's looking at whether or not your residuals have spatial autocorrelation. looking for spatial autocorrelation in your model. So when you're done, you can ask the question, if there is spatial autocorrelation, you can ask the question, is there a spatial variable I'm not considering? Or you could just do, if you have enough observations, you need to have hundreds of observations to do geographically weighted regression. But you could just use geographically weighted regression.
Hey, Dr. Raver.
Yeah.
Is the time the points start to that line, the that mean a zero if they right on that line, all the numbers, all the points together, would that be a mean zero if they close to that line?
Which one?
Any particular point on that regression line, if they're close to that line, is that close to the mean of zero? Being close to that line is just saying if you have a line going through a bunch of points, you want to try to get.
Yeah, I'm not sure exactly what you're asking, but in regression, the definition of this line, the way that line is defined is that the average of all of the distances of all of these points from the line is 0. The definition of that line. So when you ask me, does that line look like it would have all the points average 0? That's always the case. In this case, in this case, in this case, in this case. The definition of that line is the line that you pass through the data where the average distance to that line is 0. It doesn't matter how clustered those points are about the line or how close they are to the line. The average distance is always 0. Does that make sense?
Right. Yeah, I was just trying to understand that we're talking about distance to the line. It don't matter how far the points are, it's still going to be 0. So
right.
I think that the kind of pattern to it, it just gives you a number that's close to that pattern number is. Then we show you relationship with positive and negative.
Okay, so maybe you're thinking of the R² value. As the points get closer to the line, you'll have an R² value that gets closer to 1. As the points get more and more random, dispersed away from the line in a random manner, you'll get an R² value closer to 0. Does that make sense?
Yes.
So that's the R² value. But the sum of the distances to the lines is always 0. Because it's positive on this side, it's positive up here and negative up here. So the average distance to this line is always 0. Does that make sense?
Okay. Right.
That's the definite. How that line got created is by minimizing that distance, and by definition, that creates the average distance to be 0.
But if it's not 0, how would the pattern look then?
Regression, I'm trying to say that the regression creates a line where it's always 0. The distance from the line to all the residuals is always 0. Now, look, let's say the absolute distance. So in other words, these are always positive, and these are always negative differences, right?
Right.
So if we either took the absolute or we squared all those differences, that value is actually, a little bit of, it's almost exactly what the R² value is. Does that make sense? R² is almost the sum of all these squared distances divided by the total number. Yeah, in that way, you're right. As the R² value gets higher, you expect to see more points away from the line. All right, statistical check 6 is looking at the adjusted R² value. So basically, you're looking at that value at the end. It talks about the AIC. That's not on the task. So the point here is that the last check that you do is the R² check. In other words, a lot of people, when they run regression, they look right at the R-squared value and think, hey, I got a really good R-squared value. There's a lot of the variance is explained by my model. Well, but you didn't see if there was any spatial autocorrelation, which means that there's a lurking spatial variable in your data. And you didn't see if linear regression even applied to this scenario, because there's a pattern in your data that doesn't look linear. Or you didn't basically look at your variables and see how they were related to each other. I guess that's this one. Sorry, this one is. Oh yeah, you didn't see if any of your variables were related to the other variables in the model, and you were overcounting, causing bias. Or you didn't see how they were related to the explanatory variable. That's this one. Or you didn't see if any of them were significant to begin with. The R-squared is the last one for a reason, basically. All right. So geographically weighted regression, we didn't talk a whole lot about it, but basically what it does is it allows you to consider geography and creates a separate regression equation for different partitions in your study area. And so I think I said this in the class, I personally would not resort to using geographically weighted regression until I exhausted other ways to find out what the spatial relationship is. Because by using geographically weighted regression, what you're doing is you're saying, you find the spatial pattern for me, okay? And you don't even, there's a danger of overfitting, of not knowing why that spatial pattern is there. Okay? But if you find out, oh, that spatial pattern exists because as you go further from the coast, something happens, or as you get further away from downtown, something happens. And so if I can put distance in as one of the explanatory variables in my model, then I have more power, because I understand better what that variable was. I'm answering the question, does distance affect this particular variable? Whereas if I just skip right to doing geographic weighted regression, what I'm doing is saying, well, over here the pattern looks like this, and over here the pattern looks like this, over here the pattern looks like this, and I really don't have any idea why. I just know that the pattern changes over space.
So what you're saying is you should be able to observe it rather than going straight to the numbers and looking at it. You said the power of observation is probably the quickest answer.
Yeah, I mean, geographic weighted regression, in my opinion, it's like giving up on finding out why something varies over space. Like and sometimes for like big data projects, you might not necessarily be concerned about that. You just have 20,000 records from all around the world, and you just throw them into a geographic weighted regression problem, and then you come up with an equation that is different in different areas, and then you use that to basically train. So then you get more observations, and you're just pushing them through a black box. And so at the end you get an answer, and you don't necessarily know why you're getting that answer, like why that answer is different here than it is over here. But it works. Okay? Whereas using regression as a tool for exploring your data, you feed it, okay, well, I'm going to feed it a variable for how far I am from this and how far away I am from that, and you put some more effort into discovering why something exists, then you're going to be able to find out more. So it's basically just a tool for, like, if you want to find the answer for a bunch of if you want to find the answer, use geographically weighted regression. If you want to find out why, you have to think about how you can structure a model, and you're doing more hypothesis testing. You're saying, does this affect this? Well, let's see. This, you're just like trying to say, okay, well, I want my data to work, and so I'm more interested in finding that. Like, so, you know, if I was collecting a bunch of information from social media, and I wanted to find out if the probability of people buying something, well, I might feed it all into a geographically weighted regression problem and find out that, you know, in one area, like North America, people were more willing to buy it if they done done XYZ on social media, and in South America, there was a totally different equation. They bought A, B, and C. Or sorry, they'd be more likely to buy it if A, B, and C happened on social media. Okay. But I still don't understand the spatial process behind it. I just understand that it's different in different areas. There's still stuff you can pull out of it.
So you don't always get understanding and seeing a number of results, whether you're saying going through, you know, the different steps that you will look at something and then try to find out other ways. Just getting those numbers don't always tell the complete story of how you attain those numbers, right?
Yeah, I guess what I'm trying to say is that geographic weighted regression, because of the way it works. Let's talk about how it works for a second. Geographic weighted regression finds a different regression equation. It fits your data differently according to space in different areas. So it'll look at X number of neighbors and say, if you're in this area, this equation is going to work. If you're in this area, this equation is going to work. If you're in this area, this equation is going to work. So you basically end up with a bunch of different regression equations for different areas, and so you don't really understand why it's working in different areas. You just understand that it's working differently in different areas. All right.
So it doesn't tell you the why, it just gives you the results.
Well, lots of times the why question can be answered by looking at the degree of correlation, at the amount of explained variance between all of the different factors in your model. Well, this basically doesn't allow you to do that for space. It leaves that out, so you don't see how important space is. I mean, you do see how important it is, but you don't see why it's important. Okay, so that's that. So for spatial SQL, I want you to be able to understand the structure of a select command. So if you go back and look at the slides, there's like the recipe for creating a select. So there was all those like words, and then you put in stuff in between. I can pull that up here real quick.
The and, or, and all that good stuff.
Yeah. Where am I? Oh, too late. There we go. I closed Canvas. All right. This is what I was talking about, these two slides right here. Select from where group by having order limit. So what do each of these terms mean? Limit and having actually aren't on the test. So, no, sorry. Actually, I don't think any of these three on the bottom are on the test. So select from where and group by are the only ones on the test. So what is structured query language? It's a computer language that's designed solely for the purpose of asking a database and its tables questions. That's what it is. And so with spatial information, we're asking spatial data tables for its information. So when we select, what goes in between? A list of columns. So we're selecting what columns we want in the response from a SQL command is always a table. So we're asking for information from tables, and it's giving us back tables. So we say select, and we give it a list of columns that we want to see in our output table. We tell we give it a list of tables that we're going to be deriving our information from, because we might have multiple tables. If we just have one table, we just have one table name there. And then we use the word where, and we specify our condition. And by the way, the condition, that's where we specify any joins or spatial joins that we want to have happen in our data. So we could say where it's within 500 meters of a point, or where it's within 500 meters of the data in another table. And then if we use a group by command, the important thing to remember here is if we use a group by command, then we need to aggregate the data that comes back in the columns, because what we're doing is grouping a number of records by an expression. And it could be a spatial expression, or it could be, more often, it's an attribute expression, like we're grouping these by county or by some variable.
That's the one that's very similar to a dissolve.
Yes, that's how you do a dissolve in SQL, is using group by. Exactly. Good job. Yep. So how you do a spatial join or overlay always happens inside of the where condition. This just specifies what columns you're going to get, and then this specifies what layers you're going to use. If we're going to call, if this data is spatial, these are the layers you're going to use. Okay. All right. There's not a whole lot of that, but here you should be able to interpret basic SQL statements that use some spatial examples, including those with a spatial join. But these test questions are going to be multiple choice like. In other words, you'll have like 3 or 4 examples of an SQL statement, and I'll say, which SQL statement would return the total count of the tornadoes in each county. And so you don't necessarily need to know how to build that SQL statement, but you need to recognize that a spatial, because there'll probably only be one where, well, maybe 2 where it looks like there's a spatial join even occurring. And then you can whittle it down from there. Okay.
So are you talking about selecting one of the where statements, or you can use 2 of them, like maybe the where or the join, and then one of this, those 2 together will be used to determine.
Right.
You know,
yeah, something like that. All right, and then we already answered this. Group by and aggregate functions are like dissolves. They will take data and compress it, and then what you have to do is summarize. And you have to specify how you're going to summarize any column that you specify. So if you specified population and you group that by county, you'd have to say, well, do I want the total? So that'd be the sum of the population. I can't just say I want population. I have to say I want the sum of the population. You also have to specify how the polygon, or sorry, the shape features will be collapsed. Are they going to be collapsed by using the first one, Are they going to be collapsed by using the union of all of the features, or are they going to be collapsed by just combining them into a single feature, a multi-part feature? So that's what aggregate functions do. All right, and then finally last week, this one's really light. There's not much on here except for you need to understand that to do classification on spatial data, really any kind of data, you need to have 3 sets of data, or 2 depending on how you look at it. You need to have your training data set for which you know the answers, your global data set for which you don't know your answers, and then a verification data set, which is just like the training data set except for you hold it back. You do not include it in the training of the classification technique. So most of the time when classification techniques are implemented, they have an automatic way to hold out data for verification. But that's not always the case, and probably would have been good to. I wanted to actually cover a little bit of just being able to calculate this on your own, but we didn't cover that. But let's say you did have a bunch of points, right? We had a bunch of points. They represent our verification points, and those points we know the answer at those locations. We also have created a global. We've run it through a classification algorithm with our training data sets, and we have a bunch of point locations, and we know the answer. So we know the answer at some places, and we've come up with our guess at the answer everywhere. So in order to do verification, what you need to do is take those data that you know the answer and compare them to your guess at the answer using the process. And then you could, if your guess was a number, like a real number between 0 and infinity, then you could just look at the difference and come up with a difference. If your guess was a category, like in classification, you could just look at the ones you got wrong and the ones you got right. And the ones you got wrong, if you take that number and subtract it from the total, then you know how many you got right. And you could divide that by the total number of points, and you get a percent accuracy. A percent was correct in your verification process. So, yeah.
Does that mean something? The 100% means that it's close to the verification number?
Right. So if the verification number and the training number are similar, you did a good job. So if when you trained your algorithm, it said, oh, well, using this particular algorithm, I'm getting 95% of the points correct. Then you run it on all the global data set, and then you compare, using your verification data set, you compare that to your global data set. If you get 95% accuracy again, or maybe even 94 or 93, you could say, oh, I did a pretty good job. But if this one came out 95 and this one came out 65, that's pretty bad. That shows that your training method did not do a good job at actually classifying data that it hadn't encountered before. All right. So this kind of gets into why this is. You can't use verification data as training data because it will bias your algorithm and you won't really know how accurate it is. Okay? It's like giving the answers to somebody before they take a test and asking them, it really is, and then asking them to take the test, and you can't use the score they got as a valid indicator of how well they mastered the knowledge because they had the answers before they even took the test.
Almost like a false positive thing. Like if you were to use your training data as your verification data, you get a false positive, or you may get a false positive.
Well, you'd be saying, I guess in a way, because you'd be saying that this particular algorithm was really good at classifying this data when you don't really know if it was or not.
Right.
All right, so then the last one here, supervised versus unsupervised classification. So unsupervised classification is not what we've talked about up to this point. We were talking about supervised classification. Supervised classification is when you provide the classification algorithm examples. Unsupervised classification is when you ask the classification algorithm to partition the data into similar values, similar clusters.
Why don't you use the supervised or versus the unsupervised?
Well, supervised takes a lot of time, particularly, you know, you've probably heard of, you know, these machine learning algorithms and neural networks and things like that. Those are more complex classification algorithms than we talked about in this class. The random forest one is the one that we demonstrated. So those algorithms that actually try to use, basically they look at all sorts of different patterns in your data. They need huge amounts of training data in order to become accurate at what they do. They need thousands and thousands of examples in order to come up with a good classification system. So supervised classification requires a lot of effort in creating training examples. Even just statistical based methods like maximum likelihood, which I kind of talked about in that class, those require some training data, whereas unsupervised methods, they're just looking for similar values in your data, and then you can actually apply the meaning after it's done. So they come up with, oh, all of these features have the same values, and all these features have the same values, and then you could say, oh, well, we'll just call this X, and we'll call that Y. So you're assigning the labels after the classification technique occurs.
So supervised is more accurate and more expensive than unsupervised is less accurate, but it does come up with a prediction model. Both of them come up with prediction, but one is more expensive.
Well, I don't know that I would use the word accuracy at all. So supervised classification is more expensive, but it will produce the classes that you want, guaranteed. Unsupervised classification requires that you just give it data, and it classifies the data for you, and so the classes won't mean anything to you until you start to investigate the data. So it actually takes a little bit of time on the back end to kind of go through, and you know, we did this last week when we met. I showed the box plots. Well, you have to look at that sort of data to interpret what those clusters mean, what those groups of similar values even mean. Does that make sense?
Yes, sir.
All right. Well, I said we'd take about 2 hours, and we're about there. So
So if we go through each one of those questions based on how you outline them, we should do well.
right. Yep. Yeah, I would. You know, I tried to point out sometimes where I would go back and look at the slides, and I tried to point out sometimes where I'd go back and look at the ArcGIS help. And so if you do that, then I think that you'll do well on the test.
So it's kind of basic how you understand the question. If you understand the question, no matter how you write it up, as long as you got to understand what that area you pointed out means, and we should be able to
Right.
come out with this. right.
All right, any other questions?
So this last time we're gonna meet, right?
Well, we'll see each other
During the test.
during the test. Yep. But I'm available through email and through if you want to set up a office hours meeting, even on the coast, we can do it through this Skype
Skype for
for Business.
What is the code you get for this room?
0230. It's it's the office number of the office right across the hall.
Okay.
That's the way I remember it. I don't know who set it up, but they might have been thinking that.
You don't have to type it in like a cell phone. That's my first thing, is because there's 2 numbers for each code. So I thought it was like a 6-digit code because it was how many times it you not.
So it's like we're like 2 and 3 are together.
You just
Press
one.
3 usually. Just press it once and you can do it 3.
Yeah, so you press 4 buttons.
Okay.
Yeah. And now it's like something that just happened in my brain, something like that. Yeah, so you press the center button, then this button,
I saw
that
that.
button, that button. Then it opens automatically, right?
Yeah.
Like it unlocks.
You'll hear a big noise.
Yeah. That's not the code for my office door, by the way. Sometimes I forget my keys, and every once in a while that breaks. What's the code for the? Oh, you guys don't have to tell me. All right, I think I know it.
For what?
It's for the one across the hall.
I think it's the same thing.
Oh, okay.
Wow, I'm second guessing it now. My stuff's in there so much.
You know you can change it. Like you just take the screws off the back, and then there's a button to program it.
That's a good grade.
Ooh, I'll say that'd be
That's
a great way to mess with the grads.
Of course, right?